Welcome back. In this video, we're going to once again investigate the wave nature of light. In the last video, we dealt with a situation involving just two slits, and we saw that it produced a diffraction pattern on a back screen. This video will deal with a similar situation, but we're going to increase the number of slits to 1,000. In fact, the diffraction pattern produced on the back screen will be very similar to the previous situation, except now the bright spots become much sharper. We're going to combine this with the previous concept of interference from thin films in this particular problem. So keeping all that in mind, go ahead and take a look at the problem statement. Okay, so in this problem, we have a situation, a before and after situation. The before situation is that we have a diffraction grating of 1,000 slits, and we have incoming light of 700 nanometers. And as we know, in a diffraction grating, it's going to produce a diffraction pattern on a back screen. And the spacing between the spots and where they are will depend, of course, on the separation of the slits in the diffraction grating. It won't really depend on how many slits there are. We've seen the same pattern happen for two slits. The more slits you add, all it does is it makes these points much sharper, as is discussed in your book. Now, when we go to a second situation, we're going to have the exact same diffraction grating, but we're going to start adding these glass slides over every other slit. So on the first, third, fifth, etc., all the way up to 1,000 slits, on every other one, we're going to put a glass slide there. And it turns out that if you choose this glass slide, its thickness in a particular range, the diffraction pattern is unchanged. If you choose a different thickness, you actually are going to get some different diffraction pattern in these two situations. The question is asking us, what is the thickness of that glass slide somewhere between 10 and 12 microns to make the exact same diffraction pattern? In other words, I start putting these 500 glass slides on there, and this diffraction pattern looks identical. All right? So that's the first part of the question. The second part asks us if you do it in a different way, if you make the 500 rightmost slits covered with the slides, what changes, if anything? Let's answer the first part first. So to get a handle on this, and again, this kind of problem doesn't really fit quite neatly into these find the diffraction spots, find where they are, things like that. It's a little more subtle because now you have two things happening. You have a diffraction pattern, and you also have light traveling through these thin slides. So let's kind of go back a step and figure out, just remember, why are these spots occurring in the first place? The reason they're occurring is because you have phase differences between different beams of light. In other words, for example, let's take a look at this spot right here. Why is it bright? It's bright because the light coming in from all these different slits is arriving in phase. In other words, you're adding up amplitudes to amplitudes. On the same token, right in between these two bright spots, you have no light whatsoever. How is it that light's coming in through all these guys, but you have no light here? It's because the light coming in from different slits is arriving out of phase. So all these amplitudes add up to negative amplitudes, and you cancel all that light out, and that's how you get the destructive interference. So again, it all boils down to phase differences between these different beams of light coming from the different slits. Now, what happens is when you start adding these thin films, well, we saw this in previous videos. Thin films themselves can give a rise to phase differences. We had one problem where light was traveling, two beams of light were traveling, and one traveled through a refractive medium. And it turns out that by changing the length of that refractive medium or its refractive index, you can actually make the phase change when they exit the refractive medium. Let me draw that out for you, and that'll make what's happening here a little more clear. So let me just draw two beams of light, one beam that's coming through the slit without the glass slide, and then one beam that's coming through the slit with the glass slide. So, okay, well, let me draw it right here. I'll draw it as best as I can. Okay, so the wavelength is going to be whatever the wavelength is, and again, these are a little hard to draw, but imagine that the wavelength is not changing. This is a beam coming towards the slit without the glass slide. Well, I'll do the same thing in the situation where you do have a glass slide. Okay, so here's a glass slide. Its thickness is T. For beam 2, well, the source that produces this light is typically a laser source, and laser sources have the property that all the light is coming out in phase, and that's why they're so bright. So the light's coming out in phase. These guys are going to start out in phase. So I'm going to start them at the same point in the cycle, and they're going to go the same way first. Yeah, it's much harder to draw than it looks. Okay, so they're lined up until you get to this point. Now when you get inside here, what happens? When you have light traveling through refractive mediums, the velocity slows down and its wavelength shrinks. So I got to make a situation in which the wavelength is now smaller. And it depends, how much it shrinks depends on the refractive index. So it should really shrink by a factor of 1.5, but I'll exaggerate it to illustrate my point, just in a qualitative manner. All right, now once it gets back outside, its wavelength is going to be what it was before, the same wavelength in air. So I'm going to draw it with this wavelength again. Okay, so you see now that even though they started out in phase, all the crests line up with the crests and the troughs line up with the troughs, once you go through the situation where you can change the wavelength, even though they traveled the same distance, because the wavelength was different, they're now at different points in their cycle, which means they're out of phase. So now when these two beams of light have gotten to these slits, they're entering the slits already out of phase. So we have to account for that phase when we find out what these bright spots and dark spots are. This situation assumed that everything was arriving in phase. So the only phases we had to add up were the phase differences arriving, that were dependent on the path length differences. All right. In this case, we got to still consider those path length differences, but we also have to add up the phase it had beforehand. Well, this situation is saying that, in fact, I've chosen a thickness such that whatever phase was acquired here ended up not mattering at all. It ended up being in phase even when they left the glass slide. In other words, this beam traveled through this glass slide, this one traveled without the glass slide, and even though phase changes, they might have been out of phase within the glass slide, once they exited, they ended up back in phase because the diffraction pattern had to be the same it was before. So what I want to do is I want to create this thickness such that the phase that this thing acquires inside of here is the same as the phase out here, which means that the phase difference has to be some multiple of 2 pi. Why is that? Because 2 pi is an entire cycle. In other words, if you started a crest and had a phase of 2 pi, you get back to a crest. If you started a trough and had a phase of 2 pi, you get back to a trough. And that's true if you had any multiple of 2 pi. So if I had 4 pi, I get back to a trough. 6 pi, I get back to a trough, etc. In other words, I want the phase difference between wave 1 and wave 2 to be some multiple of 2 pi. So what I need to do is, as I did in the previous videos, find the phase difference and then set it equal to 2 pi times some integer. And then from that, we'll determine that the overall phase picked up in the glass slide put the wave back at the same point in the cycle that this wave was, because it's a multiple of 2 pi. So what we want is delta phi, which is phi 2 minus phi 1, to equal 2 pi times some integer. Okay. Now how do we do that? Well, we got to find the phase that are required inside this guy. The phases they pick up outside are going to be the same because they're traveling the same distances through the same mediums. So we're not going to have to worry about those. They're going to cancel out. All that matters is here where you're going to have changes occurring. So let's determine the phi 1, which is the phase picked up from here to here on this wave. The phase you pick up is always going to be 2 pi times how many wavelengths you travel. So it'll be the distance you travel divided by the wavelength in that medium. In this case, it's traveling a distance of t, and the wavelength is the wavelength in air because n is 1, so I can just write lambda there. For the second wave, it travels the same distance, but the wavelength is the wavelength in air divided by n because it's in a refractive medium, so its wavelength reduces by the factor of n. So we're going to have 2 pi times t divided by lambda over n, which means I can put the n on the numerator. So that's what you get. Now the phase difference, therefore, which is the difference between these guys, is 2 pi times t over lambda times n minus 1. And I want that to equal 2 pi times m. Okay? So solving that, you get a very simple equation telling you what the thickness has to be as a function of lambda, which is m times lambda. The 2 pi's cancel, so you get m times lambda divided by n minus 1. And because the refractive index is 1.5, this is just m lambda divided by 0.5. In other words, if you start choosing integers for m, that'll tell you the thicknesses that would give a situation in which the diffraction pattern would not change, because the phase acquired inside of here is the same phase as this plus a multiple of 2 pi, which means that they're back at the same point in the cycle. The phase is the same for both of them. So I got to just start plugging in integers, and I want to get a thickness between 10 and 12 microns. It turns out that when you choose, and again, I would just do it by guess and check, just try some integers. When you choose m equals 8, you get 11.2, which is right inside. So for m equals 8, you get that the thickness equals 8 times 700 divided by 0.5, which happens to be 11.2 microns. And that's the thickness that we have to choose somewhere between these guys to get an overall phase acquired of some multiple of 2 pi. And that means that when these guys enter, they're in phase, and when they exit, they're back in phase, because this guy traveled just a few more complete cycles. So it's back in the same point in that cycle. All right, so when I use this thickness for this glass slide, as I put these slides on here, the phase that this beam acquired by the end of the glass slide and this beam by the time it traversed the same distance, the phase has got to be the same. So it's going to give the same diffraction pattern. The diffraction spots will only occur because of path length differences arising from the spots, not because of glass slides. Those have already canceled out. Okay? So that actually kind of tells us how to answer the last part of the question, which says, now instead of covering every other slit with a glass slide, let's cover only the rightmost 500 slits. What would change? Nothing. And the reason it's nothing is because we've seen that in this situation, when you choose this thickness correctly at 11.2 microns, the phase it acquires from the point with the glass slide versus without is the same. So if they're at the same phase, it doesn't matter if you cover the glass slide or not. They're going to be back in phase when they're about to enter the slits, and you're going to get the same diffraction pattern. It doesn't matter if you cover 500 of them, if you cover every other one, if you cover only one of the slits, or if you cover 999 slits, or if you cover all the slits. You're going to have the same situation. And then again, that matters because you've chosen the thickness correctly to get these guys back in phase once it's traversed this glass slide. All right, so that's the answer to the problem. And as you see, it didn't, like I said, it didn't really fit very nicely into the equations telling us how to find bright spots and dark spots in diffraction patterns. But it did combine the exact same concepts from interference and diffraction, which says you've got to find phase differences to find out where the points of constructive and destructive interference occur. It all boils down to phase differences. So keeping all that in mind, if you have any further concerns, take a look at the attached write-up, and thanks for watching.